right, so let's just think back to our plug numbers in. So if we have an equation and we don't know what it looks like, we just plug in values. So here's some values. You pick whatever x values you want. So I'm going to start here because that's the easiest. So 2 to the 2, so 2 squared, that's 4. If I plug in 1, 2 to the first is 2. If I plug in 0, 2 to the 0, anything to the 0 power is 1. 2 to the negative 1, what's 2 to the negative 1 equal? 1/2, because it's 1 over 2 to the first, so 1/2. A negative exponent does not create a negative number. Okay, that's one of the common mistakes I see. So 2 to the negative 2, 1/4, 1/8, 1/16. Okay, now again, that's a lot of points. You do not have to plot all those points. When we ask you to plot points, we're going to make you plot 2 points that are accurate. If you want to plot more than 2, you can, but at least 2 you want to plot. So if we plot the point 2, 4, 1, 2, 0, 1, negative 1/2, negative 2 1/4, an 1/8, a 16th, the next one will be a 32nd, and so forth. You can see that shape. Okay, so the more points you plot, then you're going to be able to see the shape. But if you only plot 2, you're going to have to remember what the shape is. Now, with exponentials, would this ever equal 0? Could I ever plug in some number to make this equal to 0? No. Okay, so that does not exist, so there's an asymptote right there, because that doesn't ever happen. And so what your graph looks like is this right here, and it just keeps getting closer and closer and closer to 0, 1 over 32, 1 over 64, 1 over 128, and so forth. It just keeps getting closer and closer to 0. So it approaches that asymptote, and this just shoots up really, really fast. All right, so then the end behavior. So back to end behavior from a couple units ago. So as x approaches infinity, so as x gets bigger and bigger, so x is increasing here, and so is y. Y is approaching infinity. And as x approaches negative infinity, so as x goes to the left, this is getting closer and closer to 0. Now, there are some points that you can just remember, some like parent points whenever you plot it. You probably learned these in Algebra 2. So every single exponential is going to have that point right there, because let's think about it. If we plug in 0, no matter what this number is, we're going to get a 1. So 0, 1 is a point that will always happen. If we plug in a 1, whatever this is raised to a first power is going to be that number, so that's the base number, so 1b is always a value. And then we also have, we can say negative 1, 1 over b, that's an additional one if you want 3. But I usually plot these two, and then I just sketch the graph and go from there. But if you don't remember what the graph looks like, you're going to have to graph more than those. But those are kind of the parent function points. And then in a minute, we're going to shift them left, right, up, down, reflect. We can do all those different things. Okay? All right, so here, again, if we had those points, fine. We pick some x values here so we can just see what happens. So if I plug in 4, 1 to the 4th is 1, 2 to the 4th is 16. So 1 over 16. 1 to the 3rd, 2 to the 3rd. So 1 over 8, 1 over 4, 1 over 2. Anything to the 0 is 1. If we plug in negative 1, 1/2 to the negative 1, and we want that one going back to our exponent rules, it's just 2. To the negative 2 is 4. Okay, so you can use your exponent rules if you need to. But again, you have this point right here, 0, 1. You have this point right here, 1 base. And if you wanted this point right here, negative 1, 1 over the base, 1 divided by 1/2 is multiplied by the reciprocal. So 1 times 2 over 1 is equal to 2. So those are kind of your parent function points. You still have an asymptote at 0 because it still can't be 0. And if we plot all those points, negative 2, 4, negative 1, 2, 1, 0, 1/2, a 4th, an 8th, a 16th, 32, 64, and so forth. So that's what your graph looks like. And if you think about it, think about our transformations. If I wrote g of x equals 2 to the negative x, if I wrote that, is 2 to the negative x the same as 1 over 2 to the positive x? If I flip it, so if I move this to the denominator, I want that to be positive. I make it 1 over 2 and change the sign. Yes. Going back to transformations, if I make the x's negative, that's a reflection over the y-axis. So notice, if I reflect it over the y-axis, all those points would flip-flop. So it's kind of that transformation. Usually you see it in the form of a fraction. So if your b value is a fraction, it's going to go up and to the left. If your b, which is your base, is not a fraction, it's going to go up and to the right. So then we see as x approaches infinity, so as x goes to the right forever, it's approaching the asymptote, which is 0, because this graph can never equal 0. And as x approaches negative infinity, y is going up, so it is approaching positive infinity. All right, so that's exponents. Then we have logs. Now, logs are the inverses of exponents. And what do we know about inverses as far as x and y's? What do we do to the x's and y's? Switch them. So we just had the point 0, 1, so we switch it to 1, 0. And we had the point 1 base, so we switch it base 1. And we had the point negative 1, 1 over base, so 1 over base, negative 1. Now with logs, you have to be a little bit pickier with numbers you pick. Like with exponentials, you can pick whatever x values you want. But with logs, we can't just plug in a 3 right here. Who knows what log base 2 of 3 is? But we can plug in a 1, a 2, a 4, an 8. Those things we could evaluate if we need to. Now you're going to run out of room pretty quickly, but you could do that. Other thing, what do we know about arguments? They must be what? Greater than 0, positive. Both of those things mean the same thing. So that means it's not going to ever be 0. So for logs, we have an asymptote at x equals 0, because it can't ever be 0. Now, we can shift it. We were going to shift it in a minute. Okay? So like if we made that x plus 3 and we move this over, x could be negative 1, because negative 1 plus 3 does give you a positive argument. Okay? So when I pick my x values, I'm going to pick 1. I'm going to pick the base. And then if you want to pick 1 over the base, you can. 1 over 2. Now, you can just memorize those points, or you can plug the values in to figure what they are. So we know we're going to have the point 1, 0. Now, one way I remember that is look at this right here. Log, there's the point 1, 0, right there, LO. Okay, so that's how I remember it's 1, 0, and then I just remember exponential is the opposite of that. Okay, and then logs, L is up and down, so that reminds me that the asymptote is up and down with the L. Okay, if you need some help remembering that. Then I have base 1, so the base is 2. That means my value is 1, because really what I'm doing, log base 2 of 2 equals what? 2 to the what equals 2. I can always evaluate if I need to. And then if I plug in 1/2, okay, 1 over the base, I'm going to get negative 1. Same thing. Log base 2 of 1/2 equals what? 2 to the what equals 1/2. 2 to the what equals 2 to the negative 1. You get negative 1. Again, I couldn't pick 3. I could pick 4. 2 to the what equals 4. So when I plug 4, I get in 2. I couldn't pick 6. 2 to the nothing equals 6 that we could do without a calculator. All right, so we plot those points. 1, 0. 2, 1. And if you want that extra point, 1/2, negative 1, you can do that. And this is what a log graph looks like. Now, you'll notice on the end behavior, there's 3 blanks right there. The reason there's 3 blanks is because for exponentials, we went left and right forever. So it was negative infinity to infinity. But here we have that asymptote that's vertical now. So we're still going to approach infinity. We will never be on this side. Okay, you won't ever reflect over the y-axis. That's not a thing, because if you reflect over the y-axis, it makes the x's negative, can't have a negative argument. Okay, so you can reflect over the x-axis, but never over the y-axis with logs. So as x approaches infinity, y is slowly also approaching infinity. And then here is going to be a number. It's always going to be the asymptote. So our asymptote's at 0, and y is going down, so to negative infinity. So on these, y is always either going to approach positive or negative infinity. One is one and the other is the other. This is going to be the number, and the number is wherever the asymptote is. That asymptote can move left or right. If we had a shift down, that doesn't affect a vertical line, but a left or right does affect that. All right, natural log of x, yes?
So the asymptote is always going to be on that equation?
To start.
Okay,
Because exponential, unless we shift it. Exponential is x equals 0 or y equals 0, and log is x equals 0, always. Because it can't be 0. It can't ever equal that. Now remember, natural log is just log base e, and what does e equal about? 2.7, so that's really all you need to know. So with that one, I really would just do 1, 0, base 1. I plot those 2 points, and I just need to remember, if you want to do anything else you can, but with 2.7, it's tough to pick numbers that you know what it is. So natural log, again, there's no shifts. So we have an asymptote at x equals 0. We have 1, 0, and 2.71. And it's going to look very similar to that other one. It's just the numbers are different. Here the base was 2. Here the base is 2.7. Almost the exact same problem. Okay, it's just shifted over just a little bit. A base of 2 versus a base of 2.7. So our x approaches infinity, so as x gets bigger, so does y. As x approaches the asymptote, you'll always have to fill that in. The asymptote's at 0. Y approaches negative infinity. So again, a 2 and a 2.7 aren't different. All a natural log is a log with a base of e, which is about 2.7. All right, so those are kind of like parent functions. Now we have some transformations happening here. All right, so these first two are exponential. So when it asks for the parent equation is just the function equals base to the x, whatever this base is right here. The base is the number that has the variable in the exponent. Okay, so the way you know whether it's 2 or 3, okay, the 3 is just a shift, okay, but the 2 is what the actual base is of this problem, so 2 to the x. Our transformations, this right here moves it left 2, and this right here moves it down 3. And when we do our transformations, we always want to list them in the order of operations. So we would want to do exponents, so we want to go left first and then down 3. But if I'm just graphing it, whether I go left and then down or down and then left, I'm going to end up at the same place. Now, what I do is I like to plot my initial points. So I plot those parent function points. 0, 1, and 1, 2. Okay? If you want to do the negative 1, 1 over 2, you can do that also. 1 over base. Okay? So 0, 1, plot that. 1, 2, plot that. If you want to do negative 1 half, you can plot that. Again, we're going to ask for you to graph at least 2 points accurately. Okay, not just 2 random points, they have to be actual accurate points. You can pick whichever 2 you want. If you want to pick more, you can pick more. Now, those points move along with the asymptote. Our asymptote started at x equals 0, so I'm going to deal with that first. That moved left 2, so horizontal doesn't affect left or right, but it moved down 3. So here's my new asymptote. And then I'm going to move all these points. So I'm going to move this point left 2, down 1, 2, 3. left 2, down 1, 2, 3. And left 2, down 1, 2, 3. So there's my new points. If you don't want to graph the parent function points, you don't have to. I just like graphing them because I think it's easier. If you want to graph both the parent function and the new one, you can. Just be sure that you label which one is which. And then as x approaches infinity, so does y. As x approaches negative infinity, so x is going to the left forever, y is approaching the asymptote, which is negative 3. All right, so parent equation, g of x equals, you must use parentheses when you're writing a fraction or you're writing a negative to something, okay? Parentheses are with negatives and with fractions. Negatives and fractions. We have harped on that all year long, so hopefully by now you know that that is very important. Our transformations up here, exponents, nothing happens, doesn't move left or right, stays where it is. This reflects over x-axis, and this moves it up 3. Now that is very important that you follow the correct order. The first one, left and down, down and left, you're going to end up at the same place. But if I reflect and then move up 3 versus up 3 and then reflect, those are two completely different places. So you have to reflect over the x-axis before you move it up 3. And our points are going to be 0, 1, 1, 1/2, and if you want your other point, negative 1, 1 over 1/2, which would be 2. But again, on tests, we're going to ask you for at least 2 points accurately. But if you want to graph more, if you need to plug in more than that, you can plug in as many as you want. So we have 0, 1, 1/2, and negative 1, 2. So those are your parent function points. And now we're going to, I'm going to deal with that asymptote first. So here is where the asymptote started. If I reflect something over the x-axis, it's on the x-axis, it stays. And then up 3. So here's my asymptote. And then I'm going to take this point and reflect it over the x-axis, so it goes down to 2, and then goes up 1, 2, 3. And I'm going to actually put a little x through it so that I know I'm done with that one, so I don't get confused. And then if I reflect over and move up 1, 2, 3, there's that point. And I'm at a half. So I reflect over to negative 1/2, and then I'm back up 1, 2, 3. And that was that point. So here's what that graph looks like. So that one can reflect up or down. The half is what makes it kind of reflect over the y-axis, but we won't have any negative x's there for you. So as x approaches infinity, so as x gets bigger and bigger, it approaches the asymptote, which is 3. As x approaches negative infinity, so x goes to the left, y goes down to negative infinity. Again, these are the two that I usually graph those two. I graph those two, and then I just know what the shape looks like. Yes? X-axis.
Okay, so you're reflecting it over.
Just the x-axis. Yeah. I mean, which I guess is the asymptote. I mean, but that's not, we're not reflecting over the asymptote. The asymptote happens to be on the x-axis, so it's kind of the same thing. So these reflections are reflect over the x-axis and then move it up 3. So this point I started with right here, I have to reflect over the x-axis. Here's the x-axis, so I reflect over the x-axis, so that takes me down to 2, negative 2. Then I have to move it up 3, 1, 2, 3. Okay? Here, I reflect over the x-axis. So I reflect over the x-axis, it goes down to negative 1, and then up 1, 2, 3. And then I'm at positive 1/2, down to negative 1/2, and then up to 1/2, 1 1/2, 2 1/2. Okay? You have to do it in that order, because if I had, let's take this point, if I had moved that up 3 first and then reflected over the x-axis, I end up down here, which is not a point on that graph. has to be in the correct order. So that's why if you always just do PEMDAS for any reflections on any graph that we ever do, then you don't have to worry about what do you do first. Sometimes you end up with the right answer, but not always. Other questions? Okay. All right, so now we have some logs that we are transforming. So the parent equation would just be f of x equals the natural log of x. And remember, our base right here is e, which is about 2.7. So our points for logs are 1, 0, base 1. And the base is about 2.7 on this one. This right here, inside, so parentheses. This moves it right 3. This moves it down 1. Parentheses come before add and subtract. So I would move it right 3 and then down 1. But if you graphed it in the opposite order, you would still get the same answer on this one. Okay, but if you just always follow PEMDAS, you don't have to worry about that. All right, so I'm going to deal with the asymptote. Well, actually, no, I'm going to plot those points first. So 1, 0, and 2.7, 1. Again, if you want more points, fine, but I'm going to go with what I know the natural log graph looks like and plot it from there. So I have an asymptote at 0, and down 1 doesn't affect that. Okay, I can move that up and down all day long. Nothing's going to happen. But right 3 does. So right 1, 2, 3. So my asymptote ends up being at 3. So this point right here, I'm going to move it right 3 and down 1. Done with that. I'm going to move here right 3. So I'm a little bit off the graph and down 1. And there is that graph. And as x approaches infinity, this should be a blank right there. X approaches infinity, so does y, just a little bit slower. As x approaches, that should be a blank right there, not a negative infinity, so it should be 3. It's always the asymptote. Okay, that number right there is always the asymptote, and y is either going to be positive or negative infinity. So on logs and natural logs, y is always going to either approach positive or negative infinity, and this little number is always going to be the asymptote. All right, over here. Now, some people get a little freaked out that 3 in front bothers them, so they want to move it to the end. Plus 3 to the end. That 3 minus, okay, never in your life have you ever written a minus sign after a number. If you're looking at -3, the negative's in front of it. So that negative is attached to the log. Okay, it's 3 minus log of 4, so the 3 is a positive. So if we want to move that 3 to the end, because that looks better, looks more normal, you can. So our parent equation is f of x equals log base 4 of x. Again, that's just our parent equation. Log or natural log doesn't have any of the transformations. It just includes the base that's given. Our transformations, PEMDAS, parentheses. So left 1. Exponents, there aren't any. Multiply, there's a multiply, so that's a reflect over x-axis, and then up 3. Again, very important that we follow them in that order on this one. So my parent function points. 1, 0, always. Base 1. If you want to do 1 over base -1, you can, but you don't have to. All right, so 1, 0, 4, 1. And then our asymptote starts at 0. Left 1 affects it. Up 3, reflect over the x-axis. Does it do anything? So our asymptote just moved to the left 1. If it is a vertical line, left and right affects it. If it's a horizontal line, up and down affects it. All right, so I'm going to take this point, and here's my first, second, and third transformation in that order. So I move left 1, reflect over the x-axis. I'm on the x-axis, so I don't go anywhere. And then up 1, 2, 3. So I'm done with that point. And then here, left 1, reflect over the x-axis, and then up 1, 2, 3. So there is your graph of that function. As x approaches infinity, y is going down very slowly, but it's going down forever. As x approaches the asymptote, which is -1, y is going up forever, so that is positive infinity. So all those transformations. Now,